trajectories. So all I did was to check for each point of intersection that the product of the slopes is -1. That's the condition for them to be orthogonal trajectories. So I plugged in, because in the second one I did not have to plug in, because it's a constant. I don't have x and y to plug in. It's just a constant. But here I have -x over y. When I divide this by this, I get b over a, which multiplied by -a over b will give us -1. And the same thing for point
Where
B.
does that negative go?
Which one?
On number 1. It's negative BR over negative, or, okay, never mind, it's negative. There we go. Thank you.
No worries. So that's why we get b over a. So then the product is -1. Yes, they are orthogonal trajectories of each other. A lot of work, but that's another application of implicit differentiation, etc., etc. Okay, so from this chapter, we have 3 sections left. 3.7, 3.9, and 3.10. All we learned so far was just rules and how to apply them. But for all these 3, that's the core of the chapter. So I would like us to start with 3.7. And here we are going to look at rates of change. In different applications only. So what we learned in the previous chapter, sections of this chapter will be applied here. Let's start with a simple situation that we have all seen with motion or the particle moving such and such, rates of change in the natural and social sciences. Okay. We're not going to look at economics or biology because they will be presented basically when you take those classes. So just the basic applications. So I would like to look at an application like this. It's a long application, as you see. It's a long problem from A to I, but it's worth it. It will take us through a lot of real-life situations, then why we determine the first derivative, why we determine the second derivative, etc., etc. But I would like to start with a simple example of something like this. And then we'll come back to one. Of course, that is a very important example. I'm just looking that I have 10 minutes left, and I don't think I can finish that problem in 10 minutes. So, if a ball is thrown vertically upward with a velocity, so that's one option. A particle moves with position function, such and such. Those are potential. This we know, we've done this in chapter 2. Again, this is the same thing. We've done this in chapter 2. Yes, something like this with the volume and the rate of change. This is a perfect application of what Brian asked. When do I use this, or why do I even look at rates of change? Okay, and then we can choose others. Okay, so let's go back to a simple application first, and then we'll jump to that volume. Now, yes, we can.
Well, 10, can we do 10 within 10 minutes here?
Yes, of course. Yes, yes. And even more. Yeah. So in problem 10, is that what we wanted? Did you say 10?
You said 10 and 12.
10 and 12. 10 and 12. Very good. Awesome. So let me copy. This is S of t. T is the independent variable. 80t minus 16t squared. So they're telling us that the initial velocity is 80 feet per second, which is right here. I see it. So, and then its height after t seconds is this. And of course, it's measured in feet. What is the maximum height reached by the ball? Okay, we really don't need calculus for this, but we're going to discuss it with calculus. So T is in seconds and S is in feet. Okay, so in question A, part A, what is the maximum height? Good. So remember what we talked about when we analyzed different functions or graphs. We said, okay, if I have a function like this, till this point, the function is increasing. We discussed this a long time ago. Then from this point till this point, the function is decreasing. And then it's increasing. Would you agree with this scenario?
Yes.
And this is definitely a maximum. We're going to call it local or relative, but I don't need that concept right now. Well, what happens at this point? So see that the tangent here is positive, positive, positive. The function is increasing. The tangent has a positive slope, I meant to say. Positive slope, negative slope, negative slope, negative slope, negative slope, positive slope, positive slope, positive slope for the tangent. So when the function is increasing, the slope of the tangent is positive. When the function is decreasing, the slope is negative, and so on and so forth. But what about at this point or this point?
0.
Exactly. It's a horizontal tangent. At this point, m equals 0, m equals 0. But what is 0? It's f prime at that point, because the slope is given by f prime. That's exactly it. So all I have to do is find the derivative and do what with it afterwards?
That it's 0.
Exactly. To find where the maximum or minimum exists. Okay, can anyone differentiate this for us?
It's going to be 80 minus 32t.
That's it. Now I set this equal to 0. And we say that we are looking for, and this is for chapter 4, I'm looking for a critical number. I'm going to come back to this in chapter 4. Okay, so then I have 80 minus 32t is 0. This is what type of equation? How do I address this?
Solve across 0.
Right, so this is linear. I move 80 to the other side and divide. So I get 80 divided by 32. And if I simplify, because it's negative over negative, so I simplify by 8 and I get 10 and 4, right? And again, so I get 5 over 2. So 2.5 or 5 over 2 seconds. Okay. So I determined the time needed to a maximum or a minimum. I'm not sure if it's maximum or minimum. Who tells me that? Well, I do know because it's quadratic with a negative leading coefficient, so it has to be this. But in order to find the maximum height, I have to plug this value in the function, because this is only telling me when the particle reaches the maximum, okay, or the ball, whatever. So now S of 5/2 will be the max height. So this will be 80 times 5 over 2 minus 16 times 25 over 4. So I'll simplify and I get 40. 200 minus, I'll simplify, and I get minus 100. So this is 100 feet. But you will see in chapter 4 that this is not good enough. By determining 100 feet, I have to show that this is a maximum. In other words, I have to show that the sequence of the derivative is positive and negative. Because I could have determined this point, but the sequence of the derivative will be negative and positive. I have to show that it's positive and negative, and then 0 in the middle. So, but I do know that because the derivative is a linear function, so before 5/2 will be positive. Plug in any number, like 0. So it's positive, then it's 0, and then it's negative. So this is guaranteed to be a maximum, not a minimum. And finally, in part B, what are they asking in part B? What is the velocity of the ball when it is 96 feet above the ground, on its way up and then on its way down? Okay, 96. So in that case, we want to determine the time. So first of all, in part B, I know how to find the velocity. The velocity is the first derivative of the distance, which we already have. It's 80 minus 32t. This is the velocity. So please remember, the velocity is the first derivative of the distance. The acceleration will be the second derivative of the distance and the first derivative of the velocity. So now they are telling us that the height is 96 feet. Okay, but I don't know the time when that happens. So I have 96 equals 80t minus 16t squared to find the time. I know that this is the situation. I know it starts here. I know it reaches 100 feet as the maximum. It goes up, it comes down, and it goes through 96 at this point and then this point. On its way up, the time from here till here. On its way down, from here till here. So once I have this time, t1, and this time, t2, I can plug them in the velocity, and I'll tell you the velocity going up and coming down at these points when it crosses the 96 line height, the height of 96 feet. So I need to solve this, and then I'll stop. So I move everything to one side. This is quadratic. Okay, 16t squared minus 80t plus 96 equals 0. I'm hoping that I can divide everything here by 16. That's my hope. And I think I can. I don't need a calculator, right? So I need 80 divided by 16. Okay, so indeed, so t squared minus 5t plus 6 equals 0. It couldn't be nicer than that. I was hoping for that. So t minus 2 and t minus 3. So I have two options, t1 going up 2 seconds and t2 from here till here 3 seconds. In order to find the velocity, I'll find v of 2 and v of 3. So v of 2 will be 80 minus 32 times 2, and the other one, 80 minus 32 times 3. So this is 64. So 16 feet per second. Please remember the measurement unit of velocity is the rate of change of distance with respect to time, and this is 96. So it will be negative 16 feet per second. There is no negative velocity. It only says that the slope here is negative and the slope here is positive. This is on its way up when the function is increasing, and here is when the function is decreasing. The distance is decreasing. It does not mean that this is a negative speed. It just gives us the direction